In all these cases, the surface tension will be a major parameter. So, surface tension being a major parameter, you will find that the non-dimensional numbers, like of course Reynolds number is always present, the Weber number, and Weber number is a ratio of that is correct. So, Weber number is going to be important, it is the inertia force divided by surface tension, and also the other one is the Reynolds number is important always, which is inertia forces by the viscous forces, and there could be some other ones, which are kind of related. All right, just I have shown you before the Morton number, the Mond number, and the what is called the Ohne-Sorge number, and somehow or the other, they are all related to each other. But the key numbers is going to be the Weber number, which is the gravitational force divided by the the inertial force divided by the surface tension, and the other one is going to be Reynolds number. And but we will show you, what it is. So here the problem is that we have a liquid droplet, which is a spherical, and it is hitting a film, and that film we will change the viscosity of the material in that film to see what is the effect of the hitting of the droplet and how the shape of the droplet changes and how the viscosity may play a role, and primarily that is manifested by the Reynolds number, and the other effect of the surface tension is manifested by the Weber number. No, I mean, you can, I said that a lot of these things are related, all right, but I mean, you can choose the other numbers if you want, but the results that I will show you will just use these two numbers. But if you want to change it to Ohne-Sorge number or some other number, it's okay, but I am going to use the kind of numbers which are used in the literature so that I can compare apple to apple, all right. But if you want to choose some other number which makes sense, you can choose, and you can show the effect of the physics by choosing a different variation, okay. So sometimes you make choices based on, suppose you have experimental data. The experimentalist has reduced the data used on certain non-dimensional number. You are not going to take that data and try to create your own number and then reduce another time that. So that is the whole philosophy, okay. So anyway, this thing you can. So why this is an important problem, and I think that some of the people have asked before that the droplet impacts on solid and liquids are related to a wide range of physical phenomena in nature, like you have raindrop falling on the ground, although it may not be an important problem, but I am just telling you an example, and raindrop falling on the canal, okay. So that is where you have kind of a liquid interaction. In other case, you have a liquid and maybe solid surface interaction. So it depends on what you have, okay. And where other applications in the real world is inkjet printing and spray coating and cooling. So there are a number of applications where you have. And now, in order to show the power of the tool, we will just consider a single droplet. But if you have a spray jet coating or anything else, you know that there will be thousands and thousands of droplets. So you cannot model each of them as if it's a single droplet. So then you have to use a two fluid model or some other model to capture the gross effect. Okay, so I will keep on repeating myself that please don't think that this model problem that I am showing you to capture the effect of the surface tension via the Weber number, if you have millions of these, you cannot do this for each droplet, okay. So then you use the two fluid Euler model. Okay, and that can capture in gross the effect. Okay, so that is what is done. All right. Now the other application is like in engines, for example, that like internal combustion engine, it is actually the droplets are so small because of the atomization, and then of course it helps in mixing and creating the combustion in a powerful way. And so other one is like spray the liquid fuel combustors, cooling of turbine blades. I think somebody in the audience is interested in that, liquid atomization. And the other area that we have done work is that, as I was giving you an example a few days ago, that once you have, it's very rarely happen that you have to land on the water, a plane, all right? And but sometimes, but when you want to certify a plane that it is certifiable for flying, that test has to be performed by the manufacturer to show that in case of emergency, if you land, it can, what would be the impact on it, and which means you have to analyze the whole fluid mechanics. And one thing happens is that the moment you hit it, all the water, sprays, and a lot of them it converts, has these air bubbles formed. Not like cavitation, but in some sense, this becomes a mixture of droplets. So what we are going to do here, as I have already mentioned, that we will investigate the effect of the Weber number and the Reynolds number, and then there is a experimental data available. So those of you who have listened to me, not only in this lecture, in this particular course, but any time before, you know that I never believed a CFD unless until you have validated it. Okay, because there are so many quirks there about not only the mesh independence, not only about the boundary condition, turbulence model, etc., that if something or the other is not done right, then you can get a answer, but it can be quite off. So these are the references that are given from the point of validation. So the two parameters that will be doing it, interested is in the Weber number and the Reynolds number. Okay. So these are the simulation goals to see the effect of these. And the numbers that we have told you that are interested is the Weber number, that is the inertia divided by surface tension. And if you don't like this, and the Reynolds number, then you can combine these two, and you can find that there is other number you can create, and that is called the Ohne-Sorge number. It's very hard to even pronounce, all right. So, but it is in the literature called Ohne-Sorge number. You can see that how you can combine the two and get this number out of this. So this is our two basic numbers, and these are the numbers that we are going to be talking about in terms of the correlation. And so this is a correlation parameter, and the only purpose of that is to compare with the experimental data. And then we have the non-dimensional parameter, all right. So these are the calculations that we will do, and there is a large number of calculations. But the thing to note is that in lot of these calculations, the density that we will be using is 998.2. All right. What is it? What is its density is? So that is density of water. Okay. So it's almost water. And then you can see that Weber number correspondingly is constant, and this is the viscosity, and then these are the Reynolds numbers, this is Ohne-Sorge number, and this is that parameter which is in experiment, and this is the height of the droplet above the surface. So it could be a solid surface or it could be a liquid film, but this is the non-dimensional height, which is given by the height divided by the diameter of the bubble. So, this is the non-dimensional height H star. So, things to note here is that these are the red ones that I am going to show you some simulations, but not all of them. I mean, they are just the one that were performed. We are going to show you some simpler, some samples of some calculation. Which one? No, you can vary the U also. Okay. So, you can see that in some cases the viscosity is constant. So, in this all these cases the viscosity is constant, and in these cases the surface tension is constant, surface tension is varying, the density is constant, and this is varying. So, there is all kind of combinations that are there that have been selected some reason or the other. So, this is our problem, a model problem that you can assign to your student, to, or you can try it yourself and try to see how are you going to do in a fluent. So, this is the liquid drop, and this is the solid ground, and then there is a wall here also in the horizontal direction. And so, this is the way we look at the axis, it are turned up and down. Okay. So, this is y this way and this is x. Normally, we have y here, but please be cognizant of that. This is the size of the computational domain. These are the standard boundary condition in fluent, and this is all axisymmetric. Okay. So, this is axisymmetric pipe or axisymmetric boundary in which this is done. So, this is a very model problem, I mean, in the sense that you can actually take this and try it out, and there is a all these things that I am going to show you, we have our own technical papers published. So, if in case you need information, you want to try it, we can provide you information. If it is possible, I do not know where it is, but if the students normally know it, then we can provide you even hard data, or even if there is a UDF, like we have UDF of a lot of like models, and somebody was asked me for some UDF. If it is available, we will make it available to you. So, this is the velocity u with which this is impacting this film, and then this is the grid. It turns out that the grid has to be very, very fine in order to have a grid independent solution. So, this is almost looks like a black area which is full of grid, and then this is a very coarse grid relatively. So, you can see the coarser grid, more less coarser and less coarser, and very close to the bubble. This becomes a very coarse grid. This is a film, this is a droplet. So, this is a blown up view. This is not the same grid here. This is a blown up view of the grid here. Now, this is the ANSYS, as I said. So, it is an incompressible flow. The Reynolds number is so small, as you saw in the previous slides, that we will assume the flow is laminar. So, there is no turbulence. Explicit VOF method. Why I call it explicit? If you remember that VOF equation at d alpha over dt plus u dot alpha is equal to 0, you can solve that df dt, d alpha dt explicitly or implicitly. Explicitly is the easiest one, and if you want to make any changes, you can do that. The body force is involved. Courant number is the convergence condition in explicit case. There is time step. Now, the surface tension modeling is very important. So, you have two options actually. One is a continuous surface and the other one is a sharp model. It turns out that actually this is the reality, that if you use the sharp model, it does not converge. Now, I do not know why it does not converge, because it is in the fluent, but fluent everything does not converge, as you know. Those who have used fluent, Like if you just simply do a most simple problem of laminar flow in a pipe on a grid and you apply a second order upwind scheme, it doesn't converge. All right. But first order upwind scheme always converges. Okay. But if you want a second order solution, what do? Have you experienced this? Anybody has experienced this? Huh? No, no. Now, I mean, of course, they have bells and whistles, but most of the time, suppose you have a flow over a narrow fault and you have a high angle of attack with separation bubble. Chances are, I don't keep up with the latest versions all the time, but this is until a few years ago, the chances are that the second order algorithm, which is built into Fluent, is going to diverge. It may not diverge right away. It may diverge after 10,000 iterations, but eventually it will not converge. But if you apply a first order algorithm, I guarantee you that it will always converge, irrespective of the grid that you have. So the choice is that you have an extremely fine grid because the truncation error is of the order h and get a good solution. Or the other choice is that you go to a second order algorithm and the truncation error is order h square and get a good solution on a relatively coarser grid. So how do you beat that system? So you can beat the system that by first running a first order upwind algorithm and almost get it converged and then put it as an initial solution in the second order algorithm and then it will work. So all of us, we have done this kind of a thing in actual practice. You know that there are some tricks of the trade to make it happen. So it doesn't mean that you cannot get a second order solution or sometimes third order solution Fluent, but I am just giving you some tips that many times things happen, and of course in some simple cases it might converge also, but one single case is not a guarantee that it converges. You have to try complicated cases, a lot of cases, and then see how it behaves. All right. So like you have basically a difficult person to deal with, but sometimes that person can be very, very nice. All right. You cannot conclude on that. You have to see the behavior, most of the time to see whether, that is a regular behavior. But, I am just mentioning to you because many of you may be running that. What may happen is, so here, the point is that surface tension modeling, what we have found, at least what my students have found is that this is, now we are going to use the discrete phase model for this particular case. You could use some other model. And then volume fraction, we will use that, and which means VOF, and the second order upwind, and the second order central differencing, and implicit scheme, and instead of piezo, instead of simple, we can use piezo, which is like a simple algorithm. So these is just all the details that you need to put in the Fluent, and use ICEM or whatever it is. Or Gambit, if you have an old version, very, very old version, and then but putting in the boundary conditions correctly, etc., and having a grid independent solution. So all these things are important. So the one thing that I always keep on emphasizing repeatedly, that if you don't have a validation, your efforts, may be doubtful, not by yourself, but at least by a lot of people. So this is a validation study, which is a grid independent study, and what you see here is that there are three types of meshes: coarse, medium, and fine. And in region 1, 2, and 3, this is the size of a mesh cell. The total number of grid points is this. So it turns out that we have found that 1.1 million is good enough for the medium meshes open. But what you see here is the proof in the pudding is that if you look at the energy with respect to the non-dimensional time, and there is a kinetic energy, this is the gravitational potential energy, and this is the surface tension energy on coarse, medium, and fine grids. and there is a total energy which is in the black area. So this is sum of the gravitational, this is the surface tension, and this is the kinetic energy. And so as you can see, and this should be the case, when the droplet is dropping in the beginning, it has nothing but only kinetic energy, right, with a velocity v. So you have 1, and the potential and the surface tension energy is 0. And then as it is dropping in time or moving in time, then of course this conversion of energy takes place from here to here, all right. So, but the idea here is to make sure that what is the right size of grid and etc. So this is grid independent. So then you can say, okay, this is what I need to go forward, all right. So now this is now the validation, real validation of the numerical method, and that's where the experiments come in. So here is this experimental data from 2009 that is available in the literature, and this is a shadow graph picture of this one. So what you have in this case is that when the droplet impacts, there are two kind of things occur, and one of them is the crater. This is what is called the crater that is created in the film, and the other one is, this is called the crown. So this is the kind of nomenclature that people talk about. So right now we will not talk about the crown right now. So this is the crown of the droplet, and this is the crater that is created in the film. And so the data that we have available from the shadow graph is that of the depth of the crater and the width of the crater. So look at the crater diameter, and this is the present CFD, this is the CFD by these guys, and also their experiment, and how the changes with time. This is the depth, and this is the crater diameter, and this is depth. And as you can see it, that it basically shows that 1.1 million grid points are enough. Okay, so these are very easy actually to do. I'm telling you, these are not very difficult. But nothing is easy. I mean, once you have a mastery of the code, then you can just create the mesh, and then you know that what are the things that you have to use. And as I said, that all the stuff that I'm going to show you is on the view of method. You guys missed the level set. Okay, so you want to talk about it, we can discuss it. Okay? We had a very lively discussion. All right. No, really, I appreciate that. And I hope you had a good trip to Kashi. It's really worth it, actually. It's worth it to go there. That's very good. Where is your third friend? Oh, he's here. Okay. All right. So now this validates, the work that we have. Anybody has any question? Because this is a very straightforward application of VOF method. It's a two-phase. Now, what are the two phases in this case? It's a liquid and liquid. There is no air. It's like a rain droplet hitting the surface of the ground. Okay, so the droplet itself is not it is not air. I just wanted to make sure that we don't lose that. Okay, so now if you look at the evolution of the flow, and so what kind of solver in the Fluent are going to do this for this calculation? You are going to use the transient solver in order to do the calculation correctly. So you have T star, and this is the CFD from the paper, this is the present CFD, and this is the experiment at T is equal to 1, and so on. So as I said, you have two phenomena that occur with the impact. One is called the crater phenomena, and this is called the crown. So you can see that, and both we are comparing CFD to the CFD before, and I showed you here that their CFD and experiment is not bad, actually they are quite good. And so you see the crown development in the present work, and the crown development here at different time, and then this crater shape changes and the crown disappears in time. So, you can see that this thing is very rich in fluid dynamics, and these are very complex cases. Okay. But the most impressive thing for me is that the ability to capture this crown, which is so much of detail, so much of complexity here, is possible by VOF method. Okay. All right. Now, yeah, those guys, I don't know. We can go and look at this paper. This is the, I don't know, I mean, I will have to look at the paper. I cannot say what method. They may have their own code also. Because to write a code of this kind is not that difficult. You can write a code from scratch. If the lecture number 5, the methodology that I have described, you can write a code from scratch in 6 months. Okay. But I will not recommend you to do that unless you are really interested in exploring all the aspects of it. But if you are interested only in the physics and the calculation, when you have a solver, why you want to spend 6 months? But on the other hand, if you want to learn the method and learn how it is done, and you want to discretize the equations, apply the simple algorithm, discretize the VOF method, integrate it, the surface tension term, and do all that, then you have to do this. But I don't know what method it is. You can check it. Okay. But whatever it is, they have done a careful job. I mean, they are identical almost. And so, as the time passes, this crown disappears, and then you have basically the droplet. So, initially when the droplet comes in, you can physically visualize it. It creates a crater, but the side fluid creates the crown, and eventually, that crown then melts into the flow. Okay. So now again, now it is impacting, and it basically shows that how this impact is taking place. So this is the droplet, okay, and this is our calculation only. All the comparison is finished. So this is droplet. This is the thickness of the layer, and here you can vary the viscosity. So the first thing that happens is the droplet sinks in and creates this crater. This is the crater, right? It is half, if you take half of it, is symmetric, and then this flow on the side creates this crown, and then it sinks it further, and it then becomes a flat area, and the crown becomes bigger, and then further it becomes like this. This is a real impact. Actually, if you do the experiment, you will find that you can visualize this flow, and then you go further and further, and this may start making changes, and then this crown, as you saw in the previous slide, eventually melts and sinks down, and then this takes this shape, if you recall, and then this takes this shape, and all this droplet fluid and the film fluid, they basically start mixing in this fashion. Okay. So this is the evolution that takes place in time, and you can precisely calculate it. Okay. And the only thing is that once you have the data, you have to use some kind of a software to put in this form. Okay. So what kind of what kind of software anybody has used to display the data? It depends on it, but this kind of data, a visualization kind of data. The TechPlot is not that powerful actually. It's a good software, particularly for plotting the velocities, etc. For contour plots, is not that a great software. Actually. ParaView is a very excellent. So if you have ParaView, then I think that, or some other version of some other type, I think that will do a very good job. Okay. Now TechPlot is very good actually if you want to plot some real hard data, then it works very well. But I think that for plotting the contours, it's not that great. No, say it again now. No, no, yeah, you have a point. You see that you have a droplet with 1,000 kilogram per meter cube, okay, with some size. Now, it is surrounded by the air. Now, in this modeling, the effect of the air, you can neglect it without any problem, okay. Because if you account for the effect of the air, then the interaction of the droplet with the effect of the air surface becomes another problem. And the difference in the density, etc., is such that you are really not interested in that. I mean, your goal is not that. Your goal is to see the liquid-liquid interaction. No, it's a double phase flow, because the phase of the other liquid and the type of the other liquid is totally different. They are two different liquids, and also the two different liquids are not miscible. If they mix together, then of course it becomes a more difficult problem. So they are immiscible fluids, so that is why you see one is in blue and one is red. Yeah. So then it becomes a little more complicated problem. Water and water. Because then what happens is that the density of the water and the density of the other are so close, and the way the penetration will take place, they will merge eventually. Now, initially, suppose you have a water droplet, rain droplet, and it is going over a water surface. In the initial phases, you can see it, but afterwards, it not only it will merge. I mean, it may be phenomena in which it will merge again, but it will not be as distinctive. Okay, so from observation point of view, it will be difficult, but in terms of the physics, it will be the same. Okay, but now you have two fluids of the same density. You have the two fluids of the same viscosity. So when if you look at those relations that I have shown you, you are talking about Atwood number of 0. So what happens is that it will give rise to, it will still have this phenomena, but a lot of these things will become of the nature that more or less will not show you much of anything. Mm-hmm. Mm-hmm. Yes. No, the whole meshing has to be there. Yeah. The property in the rest of the space is nothing. There is nothing in that space. There is no fluid property at all. Yeah. No, the ground is basically captured by the change of the fluid, because conservation of mass, conservation of energy will show that how the fluid has moved. Now, software doesn't have to understand anything, because in the domain, the rest of the domain is empty. Yeah. Yeah. No, the whole domain is mesh. The whole, which I showed you in the beginning, there is a mesh in the whole domain. Yeah. No. In that domain, there is nothing. No. I mean, if you take any problem, suppose you are trying to do any problem, all right, and in that problem, when you are trying to do this problem, you assume at that time that that domain is empty. Now, let us consider a more simple problem. Okay, you have a circular cylinder, all right, and you want to calculate the flow over circular cylinder. That is the simplest problem. Okay, the only problem is that it is not that simple, because on the back side, you have wake and all that, but geometry is very simple. If you want, because a lot of you are not aeronautical people, the aerofoil is a more simpler problem in terms of the physics, but it is a more complicated geometry. But let us say cylinder. So now what you have is, how do you formulate the problem of flow past a cylinder in Fluent? No, you have let us say you have a square domain or a rectangular domain. You just take a center, you put a circle. You can put a whole circle or you can put a half of a circle, right? Symmetry. And rest of the domain you have, what is the boundary condition? Yeah, right. That's right. Yeah, but that's a simple problem. But I am trying to give you the idea, because his question was that outside the air, I mean outside the cylinder, what is the fluid? That is the question he was asking, right? What is the question that you were asking? Yeah, yeah, yes, that's correct. No, no, that is exactly the analogy that I am trying to give. When you have, I am not saying that if there is something happening inside a solid cylinder. I am saying that you have a solid cylinder and around inside a cube, or inside a box, right? Rectangular box. That is the computational domain with the solid cylinder inside it, right? Rest of the computational domain at t equal to 0, there is nothing. Which one? It's not a dynamic mesh, it is a time dependent solution. No, listen. Now what do? You apply the upstream boundary condition as a uniform velocity, pressure outlet boundary condition. In the top you can have pressure outlet or whatever boundary condition. The solid surface is an oscillating boundary condition, but the entire computation domain is empty. There is nothing there. But as t is equal to 0 plus, something start happening. And t is equal to 1 second, 2 seconds, 5 seconds start happening. And t equal to 100 seconds, you have a wake and everything, all kind of viscous phenomena and boundary layer and all those things happen. There is no fluid in that domain at the time. Oh, there is a meshing. There is a meshing to be done in the blue part. Yeah, yeah. At that point, so at that point, at that particular point, I don't remember, but you have to see that. I think because it's stationary, but the velocity of the droplet is u. So it will be basically saying that the velocity v velocity at that point is equal to capital U, because the way it is coming. Yeah. So I told you the boundary condition, when it touches the surface, the velocity of the droplet is u. So the vertical velocity is equal to u. That's the only velocity that you have. not only for that particular point, but it is the entire velocity of the whole ball of the droplet is u. Every particle inside that droplet is u. Okay. So anyway, now this shows that how the evolution is taking place as the droplet is hitting, and on the left hand side, of course, I showed you those curves, that how the kinetic energy, the gravitational energy, and the surface tension energy and the total energy of the droplet is changing as it is moving. So this basically, and the Reynolds number is, and the height, which is non-dimensional height, and the Weber number is shown there. Okay. So this is the whole process of the droplet impacting on the liquid layer. Okay. So this is again, the point here is that we can go into the details, but if you want to have any more details about the code itself, no, I mean all this stuff, the basic thing is that we are using the same concept that we discussed before. Now some of the finer details, that as you said, if we had some kind of the screenshot, maybe we could have shown that. Maybe yeah. Okay. So anyway, this shows the other details that you can do and do the calculation. Now this shows the effect of the Reynolds number on the impact process. So if you change the Reynolds number, varying from 1800 to 14,000, then you can see that how the crown shape evolved. Okay, it doesn't show anything more except how the crown shape evolves. So t equal to 0 to 17.5, and if you are able to read it, the blue is the lowest Reynolds number and the black is the highest Reynolds number, and this is a very rich set of results. But what you find here is that in the initial stages, the influence of the Reynolds number is not that evident, but eventually, there is some effect. Okay. Now, one of the conclusions that will come out of it from this slide, what is the conclusion that you can make it right now, or you can wait until the end. If you are given this slide and Reynolds number varies from 1800 to 14,000 by a factor of 10, and this is a Weber number, and you are given that evolution in time, and you see this one, what is the conclusion that we will come up with? No, but just looking at this picture, I mean, you can, of course, it's a very rich, it has a lot of information that you can extract. But if you just, looked at this, as a picture, what do you think? The thing that you see right away is that even by a factor of 10, the Reynolds number is being changed. There is not much difference. So the effect of Reynolds number is really small. So that is the bottom line that you conclude. Huh? There is a physical interpretation that the way the Reynolds number is affecting, Reynolds number has no surface tension in it, while the Weber number has a surface tension in it. So it turns out that surface tension forces are taking a much bigger. You see, what is a Weber number? Weber number is the inertia forces divided by the surface tension. The Reynolds number is the inertia forces divided by the viscous forces. So it turns out the Reynolds number, you change that ratio, let us say, keep the inertia forces same and change the viscous forces, by changing the viscosity whatever way, and change by a factor of 10, it doesn't seem to matter that much. So in the evolution of the crown and the evolution of the physical processes in the impact, the Reynolds number is not playing much role, which means the viscous forces and all that are not playing that much role. But as you will see later, the surface tension pressures are playing much more important role. So it means that in this flow, surface tension is the king. Yeah, it is. Yeah, no, I told you it's the other way around. I told you in the previous slide. Which is it? Yeah, I mean, that's right. So now what you have here, and this is interesting now. Previous slide, what did I show you? Reynolds number changed by a factor of 10. And that was a very good question actually, because we are trying to physically analyze it in terms of the forces, viscous, inertial, and the surface tension. Now the Reynolds number is fixed, and the Weber number goes by a factor of only, say 3 or 4, not too much, not by 10. You see the, look at the red guy, black guy, and blue guy. There is tremendous change in the core. Huh? No, the reason that is that the PPTs that they had, they used the Xerox machine, which is all black. Okay. No, I had told them that this is a big problem, and they said that if you do it in color, the cost is very prohibitive. Yeah, I can do that if you want to. I mean, I cannot send all the PPTs, but yeah, but I mean, that is not a part of actually. I cannot send all the PPTs without. Yeah, that I can give you. Yeah, this is all published work, so that I can give you the reference. But I think you will. I'm one thing I'm also not sure at this point. I mean, I think they are all in color, but I'm not sure that now. If you want to go to a journal and say that in the print copy, you want to have a color picture, it is at least $200 to $300 a page. Yeah, that's put in there. That you get online. Yeah, right. This is not working for some. Okay. So now there are a lot more details of the effect of the Weber number on the impact process. So it turns out that the Weber number is the non-dimensional number that is the key in understanding the physics of this problem, and not the Reynolds number. So that is the final conclusion. And of course, I can spend a lot of time in going over this and spending more time, surface tension energy, total energy, kinetic energy. But what you see here, if you that this black versus blue, that change in the Weber number changes these quantities by significant amount. So and if you did the same thing for a Reynolds number, it won't show that. So that is the final outcome, that if you have an impact of a liquid droplet and its evolution of it in time, the Weber number is the king. And I am not going to spend too much time, because otherwise you see that we will not be able to cover, and you have all this information, and eventually if you are interested, I can give you the references and as well as the other information. So again, this is the kinetic energy for different cases. again the change in the Weber number as well as the Reynolds number, and you can analyze these things. So corresponding to the crown formation, those are the bottom is the changes in the kinetic energy for these cases. Then there is some more information here. What is the energy distribution at the moment of crown stabilization? So you can look at this, and as I said, I wanted to convey the message that I did, and then you can come up with these correlations, and this is the bottom line. So the person who is looking at the final result, the answer is at the bottom, and these are the final results as a consequence of all the calculations that we did. Okay, and again there is some more comparison with the data published in Journal of Fluid Mechanics long time ago. And then you can write down a quotient to linear fit it. So there are all kind of things that can be done, all right. But the bottom line that I told you is that in this particular flow, the Weber number is the one that plays a role, and then you can see the difference. There are three types of energy: surface tension energy, kinetic energy, and gravitational potential energy, and how they vary in time, and how, and now what happens is total energy is constant. So what it means is that there is exchange of energy between these three. So the kinetic energy transforms into the potential energy, and also to partly to the surface tension energy. Okay. So this is one case. The second one is an interesting case also, and again this should be more easier to follow, because again you have a droplet. The phenomena is the same. The only thing is different is that there is no impact in this case. So what you have is a droplet, in this case a liquid droplet, and it is in a shear flow instead of a uniform flow, which means that if you have a confined shear flow, then what would be the impact? So it will be like you have a tube, and the tube you have a single droplet, not a too many bunch of droplets, and instead of having a uniform flow in most of the tubes pipes, you cannot have a uniform flow because of viscosity. The no slip boundary condition makes it a shear flow. Okay. Now the type of shear flow may be different, but it's basically a shear flow. And so what happens in a confined shear flow? Now the interesting thing that the reason I have put in, and this is our paper, but I can give you the paper number, and you can get this information. Now the breakup is the interesting part of it. Okay, that previously we never had a breakup in all the calculations that I showed you, like a breakup of a wave on the ocean, for example. So again, the applications are listed here. That is high speed spray and food processing, etc. And these are all to tell you that how the applicability of this kind of research, and then the formation of the droplet in the shear flow, breakup, and how their drag changes. So one of the examples is given is the movement of cells in blood vessels. It's a similar example because of a shear flow, and the vessel, you can approximate like a sphere, although it is not the case. It's never a sphere, but we are just trying to understand some model stuff here. Bubble infusion in the infusion tube. So these are medical applications of what I am mentioning here. So then again there is a literature available for validation, because I think it's important to do the validation, and so there are some papers available that you can use for validation. So this is the model. So this, what you have is that you have this droplet, and we are going to, for the reducing the computational time, we are going to use it as a half model in this box. or rectangular domain, and this is the uniform flow. Now, as I said, in the practice, the flow is never uniform, so you can have a laminar profile, which is shown here, or you can also have a turbulent profile, which will be a little more flatter, and then you can see what is the effect is. So now again is a surface tension driven phenomena, and we are going to assume that the flow is laminar, because the Reynolds number is such that the Reynolds number, even in an internal flow in this case, is much lower than I can see it a little later, is much around 1000 or less even maybe. So it's purely laminar flow. All right. So what are the numbers important? In this case, Weber number is very important, and as I told you before, the Ohn-Horsch number, it can be related to the Weber number and Reynolds number, and then you have the density ratio. And so the density ratio is that of the liquid and the gas. All right. So the droplet is made of liquid and surrounded by the gas. And of course, you have this other ratio, if it becomes elliptic, then you have A over B, one-dimensional time. The drag is defined by this expression. So these are all standard. And now this is the confinement ratio that was defined actually in our previous lecture, and that is the width of the channel divided by the diameter. And then you have Weber number, which is not too large, but it's the one that for the conditions that we are considering, this is Weber. Again, the numerical method is same: incompressible flow, volume of fluid. This is important. For some reason, we tried very hard with the surface that force method, to get a better interface, but the code always diverged. So it is again using the continuum surface force method, which gives a very good answer. I mean, there is no really difficulty, simple algorithm, higher order, third order, upwind scheme, same thing like previous case. There is nothing new, and it's a view of method. So all the results I am going to show you, there is no LS. Okay, but I showed actually, and you missed that part, but you can read it, that the LS and the VOF are almost the same, with very little difference. The computational methodology is the same, the integration is the same in the code. So again, as I told you, that validation is very important, because I personally will never trust anything without validation. So now you can see coarse grade, medium grade, fine grade, and then we will see that what kind of a solution we get, and this is the grade near. So what you see here is that you have the change here, this is CD, and versus the evolution of CD with respect to time, non-dimensional time, this is the total drag with respect to non-dimensional time, and this is the change in the Reynolds number with respect to non-dimensional time, and these are the initial conditions. And what you find is that a medium grade is good enough. So black and blue, they are good enough. So all the calculations that I will show you, they are done on medium grade. So these are some of the validation cases. So this is a present CFD. This is the red one is the Q et al. Q is my student actually. So I am the et al. And so you can see the comparison. This is experiment by Barba et al. And again, this is CD versus the time. And there's a very good agreement with the experiment and the CFD of previous investigation. So, all right. So we will consider this Weber number, and we will consider the case G is equal to 0 and 0.5, and then it turns out that the Weber number in this particular case of a uniform flow, it basically has a breakup earlier, so in the Weber number, and there is a breakup of the drop at a later value of the Weber number. So this is the final conclusion, and that is the critical Weber number of the droplet for breakup is different between the uniform flow and the confined shear flow. So which means that in a lot of applications that we have, whether it's a biomedical application or some others, the shear flow, the confined flow always have a shear flow. It is never uniform. It can be close to uniform, but most of the time there is some shear. And of course, if it is laminar, the shear effect is different than the turbulent. And in this case, the breakup, occurs at a different flow condition than otherwise. Okay. So this basically shows that what happens to the droplet in a shear flow and a uniform flow. And so you can see that from this movie that one effect happens in a shear flow with G equal to 0.5 is that the stretching takes place much faster, not only faster but much longer than in case of uniform flow. So it stretches rapidly in the axial direction and breaks up at the trailing edge, and its breakup doesn't occur in this particular case of Weber number of 15. So that is what I showed you in the previous slide, that at Weber number of 15, the breakup doesn't occur in the uniform flow, but it does occur in the shear flow. Okay. So this is one thing came out by numerical simulation. Now this kind of work is very difficult to do in experiment. It's a very difficult. So there is a merit to the numerical simulation. Once you know how to do it, you can do it quite quickly. And also, as I said, these are simple examples that you can do it. And if I had a a screenshot, I could have shown you that what changes are needed in ANSYS. The main thing I think is that if you can just create a grid and put in the right boundary condition, which is really very simple in this case, very simple, and just let the solver go in. The trick is in the whole thing, that if I recall, is that the time step that you take. So if you want to have a reasonable good calculation, the time step is the order of 10 to the power minus 6 or so. Those of you who use Fluent, you know that the Fluent doesn't use the non-dimensional quantities at all. That is one of the most biggest weakness. Have you used, anybody has used Fluent here that have noticed this? Yeah. So you have seconds, you have meters, and you have all this stuff, and they never use a non-dimensional quantity. So people have complained about it, but that's the way it is. Okay. So now you can see here, this is a lower Weber number. So the lower Weber number with uniform flow, which is G equal to 0, and without uniform, with a non-uniform flow or a shear flow, you can see the evolution. And what you find here is that there is no breakup, but the stretching is lower, which we showed before. So now at different times, this is a frozen stuff. Nothing, we already know what it is. Whether you have a stretching or you have a non-stretching based on the uniform or shear flow, right? And then again, you can analyze, the other properties like drag and CD and this evolution for the droplet in shear flow, which is in the red, and in the black is uniform. Okay. So these are all simple cases because Weber number is small and there is no breakup of the droplet. These are just the details, that's what is going on. So I'm not going to dwell on it too long. So now the breakup mode that occurs when the Weber number is 20. So this is a more interesting problem. So now what you see here is a uniform flow, right? And then we are seeing its evolution. And you notice here, just pay attention here. See the breakup. So you can capture the breakup by using VOR of the droplet. So it is possible to capture the breakup. So it turns out that we did one simulation, of an impact, which is not shown today, but we had to model, that the breakup in that particular case was not too many droplets, but their breakup had at least, maybe at least the simulation showed, that it was spread out of, I don't remember, maybe somewhere around 50 to 100 droplets. No, at this Weber number, I don't think there is a breakup, but there is a breakup at the in the shear flow. Which black line? No, the breakup is shown here. This is the breakup at the trailing edge. If you have a droplet, and whether it's a uniform flow or it is in a shear flow, and you have a flow going over it, the breakup will always occur at the trailing edge or in the wake region. Oh, the way I think these contours are, I don't know what these contours are made of. Uh, Most probably. Okay. So those are the contours, which represent, some velocity component or something. I don't know what this is. X velocity. Okay. So it looks like it shows that there is a breakup. I thought there was no breakup. Let me check something. Because I had those conditions in the beginning, so maybe there is a breakup. Yeah, 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 yeah. I mean, you are saying is that you have a droplet and there is a air moving it, and the air should be, yeah, it should take the droplet along with it. What do you mean by adhesive? What do you mean by adhesive force? I think that, yeah. What? No, just give me a couple of minutes, okay? I want to be done with it and then we'll go. Just give me a couple of more minutes, okay? So, let me understand, that you said about adhesive force. So now you have a droplet, okay, inside the tube, all right, and then you have the flow going over it, right. Now the question that you are raising, that he is raising it, that you have a droplet, right, and you are raising the tube, right, and you are having the flow of air. Why is not blowing away? That's the question, right. Now your answer was that there is some adhesive force. Yeah, yeah, yeah. No, no. Let us go back here. You see the problem that, I think, no, 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 no. This is the problem that we have. Okay. This is the original problem that we are having. And this is the droplet. Okay. What is wrong with this problem? That is what I am trying to understand. Suppose you are trying to calculate the flow over a lift over aerofoil. All right. You put the aerofoil in the wind tunnel and you blow the air. It should blow away, right. There are a lot of experimentation that have been done. If we use the same logic that you have, they should all blow away. Yeah. So similarly, this is a model problem in which we are not talking about the mechanism that is holding the droplet. All right. We are not talking, like, when you do, suppose you, let me do this. Let me say to this. Have you ever done any calculation of a flow over a object? Have you ever seen a flow over a cylinder in a paper with a visualization? There is a cylinder, right? I don't care whether computation or no computation. Experimental visualization of a streamline, right? If you look at this, is there any description there that how is it been held? If you do the simulation, do you consider it that it has been held by something? In wind tunnel, I agree that when you do the experiment, you have aerofoil and you have to anchor it, all right. But when you are doing the simulation of the flow over an aerofoil, you consider it is an infinite fluid. There is no anchor, nothing, and the flow is coming in with a boundary conditions, and you calculate the lift. Why is not blowing away? Because you are interested in the part of the problem that the aerofoil is experiencing the lift, experiencing the air, that is creating the pressure differential to create the lift and creating the drag, and this is the physical model that gives you that answer by the governing equations of fluid dynamics. Okay. You are not considering at that point that why is it not flowing away? Why is not running away? I don't understand that this is a model problem. No, no, you have at t equal to 0, you have a liquid film, a liquid droplet. You blow the air and in course of time, how it is deforming. That is the model problem we are solving. Okay. Now you are asking the question that how you are doing this in experiment, or or how it is not blowing away, what is happening. That is not our objective here. Our objective is that you have a confined flow. Upstream, it is the flow has some kind of distortion, or you can say some kind of non-uniformity instead of being a uniform flow or a shear flow, and how this droplet of liquid is deforming in the presence of the air, and we are taking symmetry also. Okay, we are not assuming that it's not symmetric about the z-axis to keep it simple. All right. Otherwise, you can also do another problem that make it closer to another, closer to the one of the surfaces, and then you can say, okay, then you have to do the whole droplet instead of half. Here the goal is that to see numerically what is the effect of the flow of air over the liquid and how the deformation and distortion takes place. The key parameter is the Weber number and how the breakup takes place. So, that is the model problem that we are studying, all right. And now you are, then you are bringing the things which I think is peripheral, because as I told you that even if you read a book on this subject, they do not consider these other peripheral. There is not a single problem which is really two dimensional in the real nature. You do not have a two dimensional in real nature, right? But we have a two dimensional flow because the other dimension is not that important. Am I answering your questions or not? Okay, what we are going to do is, let me finish this. We can talk about outside when we are having a coffee, because otherwise we won't have a break. All right. But let me tell you again and again, we are doing this model problem, and please don't bring in this question of this adhesive force and this force and that force, because they are not relevant to the problem that we are doing. I am willing to entertain the question, and I am trying to explain. Now, if you have an objection to my explanation, then we can discuss it further. So, let me just take a few more minutes and finish this. So, now there I agree that there was a breakup, that because when I look at it, at Weber number of 20, there is a breakup in the front in the case of a uniform flow also, and your observation is correct. That is correct. Yeah, I don't know, but I agree with you that it should be at the trailing edge. So, in just like in this other case that you see here, so no, it is not a breakup here, because the Weber number is 10. So, it is only 15 and 20, and in one case, I think it is it's a very different time. I think this is the only I have shown actually. I am just repeating it. This is all repeat. Yeah, so this is the one that we had a question. So, here you see that the right hand side, this is the correct thing. In the left hand side, you think that there is something has broken up and the black circles and is going over there. Yeah, I don't know what is happening there. All right, but the correct answer is that it should be on the right side, and you can clearly see that in the non-uniform flow, it is on the right side, and it has to be at the trailing edge. Now, why that is showing up, and why what the software is doing there on those contour plots, I really do not know, but physically I know the answer, that is correct. And this is correct actually, the breakup is taking place at Weber number of 20. Yeah. So, again these are some other. So, you can now see what is the critical value at which this breakup can occur. And then now you see that this one, if you look at it, for a various degree of confinement, which is denoted by G, going all the way to this, and then you can see the time, and then you can see that how this breakup is taking place, and then basically creating a vortex downstream. So, now if you look at this one, you can clearly see the difference. So, this the droplet that is behaving at G is equal to 0, it is more like a cylinder. So, it is a flow past a cylinder, and you have this vortex, and if you look at G is equal to 0.5, you have a little vortex, but it turns out that at a later time seems to disappear and merge into the droplet itself. So, these are the physical phenomena that you find that occur in case of confined shear flow. So, let us see what is saying is that compared to the uniform flow, the critical Weber number for breakup, it decreases in confined shear flow. So, it means that the breakup occurs much faster. The droplets in confined shear flow suffer a smaller radial deformation, but larger axial deformation, which was shown into the video that we had. And then of course, it occurs in Weber number of 20 in both the cases. And so, whatever we have discussed, you saw in the so we are going to take a break here, and if you want, we can show you this head-on collision of two droplets, or if you had enough of the droplets, then we can move on to the other topic. No, we are having a break, but after